Okay, we're back to Chapter 3, Fluid Statics, and today we're going to be discussing the fourth section in this chapter on center of pressure and hydrostatically equivalent forces exerted on panels, flat panels, and we're going to describe how pressure is related to pressure force. So section 3.4, we'll just skip ahead here through the sections we've already done. And we're going to start here. The first thing that I want to discuss is how pressure distributions enact forces on objects. And so really the major points of this section are to relate the pressure inside a fluid to the forces that it enacts on objects, and to determine how to calculate these hydrostatic forces on, in particular, flat panels or flat surfaces. And so let's start out with a description here. What we have from the book here is a figure of a cylinder inside a flow field. You can see that there's some flow coming through here. This might be, like a rock in a stream or something, and you've got some vectors that are showing the velocity coming through here, and this dashed line here is showing what the pressure might be around that cylinder. And so you can see that the pressure at the front of the cylinder, as the flow comes in this direction, the pressure here is larger than the pressure back here. This pressure distribution is called a non-uniform pressure distribution because it's greater in front than behind the cylinder. And also, you can see, if you remember, that you can see that the pressure force, or the pressure on the cylinder, is compressive. This is a key point. And we saw that when we were talking about hydrostatic pressure. So any pressure in a fluid is going to be compressive. And so at each point, the pressure vectors are normal to the surface of the cylinder. And if we look at that in more detail, if we just look at one little small area, differential area on that cylinder, we see that the normal to that surface is vertical here, this unit vector here, but that the force being enacted by the pressure onto the object is in the opposite direction. Therefore, you get a minus sign in this equation. So a differential force element here, dF, is going to be equal to minus the pressure times the unit vector, and which just has a magnitude of 1, dA. So, and then obviously to get the total force across this whole object, and in fact, if it was this in this pressure field, we would have to integrate around the whole cylinder, all the pressures at through all the differential areas to get the total pressure, the net pressure, due to the pressure distribution. So let's look at a couple of different cases. Here we have a case where we have what's called a uniform pressure distribution. This is a uniform pressure distribution, and as we look down across this panel here, we see that all of these pressure vectors are the same length. Now this might be, if we kind of turn this on its edge here, so that these lines were pointing down vertically, this might look like the pressure distribution at the bottom of a tank of water, like we discussed in class. And so this is a uniform pressure distribution, so the pressure is the same across this whole panel. And what we can do then is we can show that, we will show that the pressure, the force resulting from that pressure, can be enacted along a line of action through the centroid in the case of a uniform pressure distribution. And we can basically, this resultant force, Fp, will be that force acting on that panel. And that has to go through what's called the center of pressure. And that's true for a non-uniform distribution, which we'll look at in a minute. But for this one, the center of pressure actually is coincident with the centroid of this panel. And so we have these uniform pressure distributions, but in the case of a hydrostatic pressure distribution now, this is non-uniform because we know that as we go deeper down into a fluid, such as this one here, that the pressure will get greater and greater and greater down at the bottom. And so what we have, the forces on this panel here, are such that they have to be normal. Remember, it's a compressive force. So this force up here enacting on this corner, this top edge of this panel, is less. It has a smaller magnitude than the force down here, which has a larger magnitude. And so this, what this does is it says that the line of action now is no longer coincident with the centroid, that the center of pressure on this panel where that resulting force acts is actually deeper, further down on the panel, deeper in the tank. So we can see then that the center of pressure is not at the center of mass or the centroid of the panel any longer. And this is because the hydrostatic pressure distribution is not uniform, that it increases with depth. So now what we want to do is take some time to go through understanding the forces in detail on a gate or a wall or a dam. This is a great example here of a panel at the bottom of a tank. This might be at the bottom of a dam, so this might be under tremendous pressure. And so we need to look in detail at how we deal with these forces. And so what we have here is this picture. This picture takes a little bit of explaining. What we have initially, what we're going to look at initially, is the panel on edge. So this is the edge of the panel, and these are the forces that are being enacted on this panel. So since it's in a hydrostatic situation, the pressure at the top is less than the pressure at the bottom. Now what they've done graphically here is they've taken this panel and they basically laid it out in this way so that we can look at the face of the panel as well, so that we can see what shape it is and how we might integrate a differential area across the panel. And also, in addition to what they've done is they've created what's called this slant path here, which allows us to measure basically these distances from this reference line. This is basically a reference line in kind of a rotated frame of reference, but this is a reference line from which we make measurements. The y value just tells us how the location, the vertical location, if you will, from this line of our differential element dA. Y bar tells us the distance from this reference line down to the centroid, and YCP tells us the distance from the reference line down to the center of pressure. So the key here is to really determine, using this geometry, and to determine where the center of pressure is relative to the center, relative to the centroid. That's one of the things that we will do. So you can see that in order to find the total pressure on this panel, we will have to take these differential areas, dA, and we will have to run them all along the panel here, and we will have to know the pressure on each of those panels. And you can see, if you look at the edge now, you can see that the pressure across this for any dA at any y is going to be constant because it's at a constant depth across this. And that's what's important, is the depth. So let's see. In addition, I want to make sure that you understand that that this is kind of two pictures of the panel. One on edge, which shows that at each y value here if we were to look at different y values, at each y value, the pressure across the panel into the page is going to be constant at a given depth here. So one of the things that I wanted to show was that this geometry here is such that the depth of the fluid is related to both y and this alpha. If we construct a triangle here, over here, let me just do this right here. We construct a triangle with alpha here, that's an alpha, and our y value, remember, is measured along this line. So this might be y, but that doesn't tell us the depth. The depth actually is going to be this line right here. This is z. And so z is, let's see, z over y equals the sine of alpha. And so to get the depth, which is going to be very important for us in hydrostatics, we note that z equals y sine alpha. And this is something that we're going to need. So even though this is kind of a strange diagram that kind of splays out the face of the, kind of splays out the face here, we can see that really what matters for the pressure is the depth from the top of the fluid down to the differential element. So it's kind of a confusing diagram. But let's mosey on here and go to the next slide. And what I'm going to do next is I'm going to do two things. We're going to basically integrate across this thing for each differential element. We're going to come up with an equation to integrate this up, and we'll find that it's quite a simple solution to get the force on the panel. It turns out to be quite an easy, and basically what it is the pressure at the depth of the centroid times the area of the panel. And we'll prove that, and then the second thing that we'll prove is, or that we'll find, is the difference in the distances from the center of pressure to the centroid, and we'll see that that's equal to this equation here. So basically we're going to find the difference in the distances between these two things, and if I can draw just a little line here, it's going to be this distance right in here. So we need to find the center of pressure relative to the centroid. That's going to be important for doing problems of this type.